I've already wasted too much time. Periodic properties means properties that repeat. The periodic table is called the periodic table because after every 8 things, it repeats itself. There's subtle changes, but it repeats itself. And it's ultimately because of valence electrons, which we've learned about. Everything in family 1 has 1 valence electron, so chemically behaves the same. In 2, it has 2. We skip the D for a while. We come over. These are the representative. S and P are the representative elements, the ones that behave the way we hope that they do. All right. Family 3 has 3 valence electrons. They all have them, so they behave the same. 4, 5, 6, 7, and 8. But after 8, it goes to 1, right? And so then it drops down and it repeats. So it's ordered by its periodicity, or that the stuff repeats itself. Okay, here we go. I'm ready. What? We don't really worry about the radioactive stuff. All right, this is directly from the AP class gigantic 200-page book that describes how to teach this. There's not a ton you need to know here, except for this entire chapter covers this SAP 2-A, which is weird because it's actually in the first learning objective, but it has a 2. I don't even get it. And really, it's right here. So this is what we're going to learn in this unit. It is the trends in the atomic properties. So it's pretty simple to me and hopefully not that hard to you. There are 3 things here that help us explain these 4 things here. And that's all we're going to do. There's more to chapter 7, but we're going to talk about these 3 things, and then we're going to say how it affects these 4 things. Fair enough? We're just getting to the bare bones. It's probably better in the long run. So trends in atomic properties within the periodic table can be qualitatively understood. That means not math, no math. All right, through the position of the element in the periodic table. Coulombs Law, the shell model, and the concept of shielding / effective nuclear charge. These properties include. So if we know where something is and we know these 3 things, we're golden. We can use that to explain any of these. Ionization energy, atomic and ionic radii. Oh, I deleted a slide because I didn't even notice that it said that still. It's okay. We'll live. I'll fix it. Electron affinity and electronegativity. All right. Of these, all 3 of these are really important. And this one is kind of not really important, but it's still something that we teach. Okay. The periodicity is useful to predict or estimate values of properties in the absence of data. So if we don't have actual data, we can look at it and think, oh, okay, well, I think sulfur is going to behave this way because other things did this. Fair enough? Okay, kind of annoyed that I didn't even notice it said ionic. Here we go. Oh, I forgot. I made this a bigger slide so you could read it easier. This is the key. So we know how to find where something is on the periodic table. So I didn't review that, right? You just, if you know its name and symbol, you can just find it. You know where the metals are, you know where the non-metals are. You know the F's, you know the P, you know the D, you know the F's, hopefully. All right, so we went straight to Coulombs Law, which we already went over, but it's pretty important to understand so you understand how things change on the periodic table. So Coulombs Law is the attractive or repulsive force between the, oh, I edited this. There's no repulsion. It would be the repulsive force between 2 electrons, which we'll talk about too. Between the outermost electrons and the nucleus, it is directly proportional to the magnitude of the effective charge of the nucleus and the electron, and inversely proportional to the distance between them. This effective charge has a name, and we're going to learn about it. It's called Zeph. All right, and we'll learn about it, but don't stress. So what? It's because Z is equal to the number of protons in the nucleus. All right, well, we're going to go over this. Z is that, which you would think, hey, if it's element sodium, Na is 11, it would be 11 plus. That is Z, but Zeph, the effective nuclear charge, is only going to be 1 for a reason that we're going to talk about. But so Z means protons, like the nucleus, and effective means once we apply this shielding or screening effect to this whole substance. So that's where it gets that. All right, make sure you remember Coulombs law is F is sort of equal to, we're ignoring the constant, that's why we don't just say equal to, Q1, Q2 over D squared. R or D is fine. R means radius, D means distance. They're the same thing. It doesn't mean diameter, though. I guess I should be careful there. All right. So and you can put R if that's more clear. So it's the Zeph, which we'll learn more about, times -1. Why -1? Because that's the charge of an electron. Okay, we can do this for the repulsive force between two electrons, and then it'll be -1 and -1. We can do that too. But for now, just with this, divided by how far they are apart. So, Coulomb's law, the force that the atom attracts its electrons is equal to the, roughly equal to the effective nuclear charge times -1, essentially, divided by how far apart they are. So the charge of the nucleus and the distance between the electron they're going to govern everything that we're going to talk about. The effective nuclear charge and this distance. Okay, so I've said it 10 times. What is the effective? Oh, sorry, we're getting there. I got to define the three things and then we'll get there. Sorry. The shell model. The shell model is great. It helps a lot to picture things, but remember, the atom's really the like just scribbly jumbled mess. But this is an easier way to look at it. In this model, electrons, which are negatively charged fundamental particles, in atoms are thought of as occupying diffuse shells in the space surrounding a dense, positively charged nucleus. And then this is important, and it should be common sense. The first shell is the closest to the nucleus. We kind of already went over this when we had this graph right here. Right? And the binding energy of that one was bigger because it was closer to the nucleus, which meant D squared was small, which meant force was large. Sound familiar? A lot of people got this one wrong. But we've sort of already talked about this. So in the shell model, we have the nucleus, we have the electrons going around in these concentric circles or spheres. They overlap each other, whatever, yada, yada, yada. But the first one is close and the seventh one is far. Looking at the periodic table, we would say that hydrogen, its proton and electron are really close to each other because it only has one shell. I'm going to say in francium, the proton and its outermost electron is like right here. Now there's a bunch of shells in between, but it's really far, right? Really far out there. Okay, so we're going to learn this distance, even though they have the same effective nuclear charge of +1, the distance is going to matter here. And Coulomb's law says if the distance is really large, the force is small. So how hard would it be to remove an electron from francium? Not hard, because it's way out there. That's kind of the Home Alone model. Did I tell you about that before? Yeah, they wouldn't have forgot what's his face, Kevin, if they had one kid, but they have 87. It's easy to lose one at the airport if you got 87. Okay. Okay, fair enough what the shell model is. Okay, so tell me right here. I'm going to say I have a red one. Actually, tell your partner, not me, and a blue one. Which one is more attracted to the nucleus and why? Tell your partner now. Okay, red because it's closer. Red because it's closer. That makes the distance smaller, which makes the force larger. Be okay with that? That's what the shell model is. So we have back here, we have the position of the element, That's just finding where it is. Coulombs law, directly proportional to the charge of the nucleus and inverse to the distance. The shell model says we have concentric rings. And if you're close, high, out, low. And then the shielding. We'll get into shielding after we do, well, while we do Zeph. So here we go. Every part of this chapter has something to do with the effective nuclear charge. Every part of it. So it's super important that you understand what the effective nuclear charge is. Now it's going to be a positive number, and I'll spoil alert, it's just the family number. Everything I'm going to say, if you get lost, the effective nuclear charge is the same as the family number. Okay? In the next 5 minutes, confused? Remember, it's the same as the family number. What else have we taught or learned was equal to the family number? Valence electrons. All right, the valence electrons. They are definitely, it's the same number, so they must be related to each other somehow, most likely, right? Okay, here we go. In a many electron atom, and that really just means more than one. So hydrogen, we don't have this, but we don't need to. We only have one. So next, in a many electron atom, electrons are both attracted to the nucleus and repelled by the other electrons. So it's actually kind of a balance. You have a nucleus, you have an electron that wants to be attracted, but if you have core electrons right here, it's pushing it away a little bit. Okay, and everything we're talking about is the attractive force between this electron and that nucleus. And it would be really easy if this part didn't exist, but it does. So this is why we don't say the nuclear charge, because that's just equal to the number of protons. We say the effective nuclear charge, which means we're accounting for the number of electrons that are also pushing away. You kind of with me? I know you're like, man, you're going fast. Well, I am trying to. Okay, so the nuclear charge of an electron experience depends on both factors. All right, now here is just the English version of what the effective nuclear charge is. It's the attractive force between the nucleus and the outermost electrons. I think I typed that, or it's written, right? So we're fine. What's that? It's how hard the nucleus pulls on the electron. But it's got to pull through a bunch of other electrons, so it's kind of tricky. Okay, this slide has a lot of words on it, but it's pretty important. We're 1/4 the way through. I feel good about this. All right. The effective nuclear charge, or ZEFF, which we will refer to it as Zeph most of the rest of this chapter. The effective nuclear charge and Zeph mean the same thing. Is found by doing the following math. And I know, like you said, there wasn't any math. Well, there isn't, because you're just going to memorize that Zeph is equal to the what? Tell your partner. We already said it. The family number. And it is equal to the family number because of this. Zeph is equal to Z minus S, where Z is the atomic number, also known as the number of protons, and S is the shielding constant, usually close to the number of inner electrons. And for us, we're going to say it is equal to the number of inner electrons. Now, inner electrons have their own name. They are called core electrons. Yes. I have no idea. And you're like, whoa, okay, dummy. It always has been my entire life. So I don't know. Okay, so it's pretty easy. You take the nuclear, or the atomic number, I mean, and subtract the number of core electrons. So the core electrons, so for sodium, Na, it has 11 protons. to find the core electrons, I go back to the previous noble gas, which is neon. And what's its atomic number? 10. 11 minus 10 is plus 1. It's in family 1, and its Zeph is equal to positive 1. Yes.
So say we're doing like oxygen.
Okay, oxygen.
Would you say 16?
I have 8 electrons, right?
Yeah.
That's okay.
16 is the number that's above it. So
I know. And then what's the previous noble gas? Neon. Or sorry, helium. Sorry.
negative 2.
So it is 2. 8 minus 2 is 6. That's its effective nuclear charge. Carly, you're making a face. Do I need to do more? It's okay. Let's do another one. So we had Na was equal to plus 1. Whoops. We had oxygen plus 6. Magnesium. Magnesium is element number 12. The previous noble gas is neon. So 12 minus 10 is plus 2. I'm going to do the same thing, but say it in a different way. I'm going to say it in a different way. You with me? All right. So aluminum, sorry. Aluminum is element number 13, right? Can you tell me how many valence electrons aluminum has? 3. So that would mean how many core electrons? 10. Oh, it better not be, because the nucleus is made out of protons. So did you see how I said it different? Instead of saying the previous noble gas was neon, which it is, and that's 10, that's fine. I said, how many valence electrons did it have? And I took that away to get 10 and got 3. Now, how many valence electrons did it have? 3. What's this answer? It's the effective nuclear charge, and it's the family number. How many valence electrons does sodium have? 1. Magnesium, 2. Oxygen, 6. And it's the family number, so it's a big chemical love triangle. Effective nuclear charge is just equal to the family, because it's all of them minus the core, which is the same as the valence, which is what the family is. It's just, they're all the same. Okay, so without doing math, what's the effective nuclear charge of Se? Tell your partner. It's plus 6, because it's in family 6, right? All right, what would we have if we had Ar? It's weird. It's 8. You're like, wait. Yep. Now look, they're not going to make you do it, but you do need to know that it would be 8. Okay, now coming back here. Here's some explanation that's kind of important. You don't have to explain this part on your AP test by any means, but it kind of helps. So electrons in an atom can shield each other from the pull of the nucleus. So the nucleus pulls in, but electrons push out. They push other electrons out. This effect, called the shielding effect. Do you remember that from earlier? That was in AP, that you had to have shielding effect / effective nuclear charge. The shielding effect is when electrons repulse other electrons. They push them away, even though they're being pulled. Okay. Describes, the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. The more electron shells there are, the greater the shielding effect experienced by the outermost electrons. Okay, so The shielding effect explains why valence shell electrons are more easily removed from an atom. So if you have your nucleus, you have your 2 electrons, that fills the first shell, right? And in the shell model, the next one would have 8. Okay, I don't do this very often. Whatever. I'm just going to fill it halfway. So it'd have 2 S's and 2 P's. Okay. So this electron is both attracted to that nucleus and repelled by these electrons. Now these are not repelled by anything between them and the nucleus, right? And we learned these have a higher binding energy. We learned that because they're harder to remove. This would have less because it's easier to remove, or now because it feels less force because it is shielded by the others and pushed away a tiny bit. Okay, so it's a balance of all these charges. All right, so summary so far. You got to get these. Zeph is the attractive force between the nucleus and the outermost electrons in an atom. This is written on there, right? Okay, the periodic table, I was pretty proud. I drew that with the line tool without ever fixing a line. Zeph increases from left to right on the periodic table. So if I were to put an arrow, which you need to put an arrow, Zeph increases from left to right because we are adding protons, but the number of shielding or core electrons stays the same. So Zeph for family 1 would just be +1. Family 2 +2, all the way over to +7, +8. We don't worry about the noble gases very often, but it should be easy. If it's equal to the family number, as I go from the left to the right, the number got larger. Yes?
What do you do with transition?
We ignore them. But it's fine. It's a general trend. So we could say that this over here, gold, silver, platinum, they have a higher Zeph than over here. I don't know those. Scandium, yttrium. What's that? Yeah. Now, these trends are not absolute. They're a general trend. There are exceptions, and we'll visit them, but not stress about them. Okay, so you absolutely need to know the trend for Zeph increases from left to right. But what we really need to know is, what does that affect that I actually see? And we're going to talk about that. Well, is it the next slide? Am I in the right order here? Okay, yeah, we're coming. All right, so this explains Zeph from the left to right. Large Zeph to the right. Now, because as we move down on the periodic table, we are adding principal energy levels or more shells, we get larger atoms. This is probably out of order, but that's okay. And there is more electron-electron repulsion. Now, I need to say something. When we talk about the up and down and the change in like Zeph and size, make sure you realize Zeph affects your left to right. We're going to talk about size, and up and down has very little to do with like the shielding constant and all that jazz. It's all about adding a shell. All right, here we go. So I'll come back to that slide in a minute. It should have been later. So sizes of atoms. This is our first application. I'll come back here in a second, but we had this straight from AP. We needed to know these things. So we have atomic and ionic radii. That means size. Radii means their radiuses or how big they are. So when we have an atom, we measure from the nucleus to the outermost electron, or half of the circle, which we call the radius. You okay with that? Okay, I'm coming back. But now Now we're making the money. We've gone to school. Now we're going to go work. All right. So the atomic radius is defined as 1/2 of the distance between covalently bonded nuclei. And that's a complicated way of saying it, but it's good enough. If you put two things together and they bonded and you measured between the nucleus, half of that would be the size of one of the atoms and the other half would be the size of the other. Fair enough? Okay. Now, this is really important. Bonding atomic radius tends to decrease from left to right across a row on the periodic table. And you have to absolutely know why. That's due to increasing Zeph. Okay, so as I go from here to there, I get bigger. So if I were to draw the size of rubidium or francium, I'd put like that. If I was going to put helium, I'd put a really, really, really small dot. If I was doing it in the same row, it looks something like that. Okay, this is important. We talked about the position and where it is. We talked about the effective nuclear charge. We talked about Coulombs law. We talked about the shielding effect so that we could understand why this ultimately happens. And that is because Zeph increases. So Zeph, that's an E. Zeph is big here. Zeph is small here. I don't know. So think about it. If, let me describe Zeph again. If Zeph is how hard the outer electron is being pulled, then the bigger Zeph, the smaller the atom. The bigger Zeph, smaller the atom. They're inversely related. Oh man, I'm losing everybody. If the electron is not as attracted, it's farther away. That's, if I put that again, if Zeph is small, I'll put that again. If the electron is not as attracted, the atom's bigger. Remember, the positive nucleus attracts the negative electron. The more they attract, the closer they are. The more they attract, the smaller the atom. Tell your partner right now, finish this with me. Non-metals have high, tell your partner, Zeph, and small atomic radii. I would put that note or in your notes. You just drew it, but I'd put it as a sentence. Non-metals have high Zeph and small atomic radii. Now, you could write the same thing about metals. Metals have low Zeph and large atomic radii. You don't have to write that down, but I want you to read what you just said for a second. And then we're going to tie something together I think I've said before. Have I said something about something being a loser before? In a non-hurtful way. All right. We said metals are losers. Tell your partner why they lose electrons. Got it? Okay. All right, let's come back together. Metals are losers. There's a few ways to say it, but why? Smaller Zeph, bigger size. It's easier to remove an electron. They have no interest in gaining electron. None. Okay. Zeph helps explain a lot of things. One of them is the size. Now, there's two parts to this because the periodic table isn't just one 120 box flat line. There's also up and downs, right? Okay. So the arrow points down as well. This one's usually not hard. The size of the atom, the atomic radius tends to increase from the top to the bottom. And that is because we're adding shells. And that is really it. There's a little bit more to it. There's more electrons to push each other away. But ultimately, it increases from top to bottom because we're adding more shells. AP wants you to know the shell model, so you should use the word shell in an answer if you're asked about why lithium is significantly smaller than cesium or francium. And you'd say because francium has more shells than lithium. And you can go more into depth, but that's the easiest, shortest, and it's still right. Okay, are we okay? So far, and you don't have to do this, but it could be helpful. Whatever. So far, Zeph increases as I go this way, right? All right, that's one trend. Radius, whoops, whatever. Okay, that was ugly. It is large as we go here and we go here, right? You should be able to know both those trends so far. You should know how the bottom trend relates to the first trend as well. Okay. We feel okay with that? Okay. I am dumb and deleted the next four slides. So here is what we're going to talk about. Size of ions. Well, I'm going to say size of ions versus their parent atoms. Okay, so put this somewhere. I'm sorry that I rudely, I just said I'm an idiot. Because even when I deleted, I'm like, I've taught this so many years, it's not even on the AP test. Like I knew it was, but whatever. Okay, this is not a super hard thing. And you don't need to know the trend. You just need to know what happens here. So does anyone remember what a cation is? All right, good. Cations are the metals. And there's more to this sentence, so don't write this. They're the metals that become positive, right? You with me? You with me? Okay. If they become positive by doing something, tell your partner what they did to become positive. They lost an electron. Okay, so I'll come back to this, but just a simple model. We have our nucleus, we have our shell. All right, and we're just going to do this for lithium. It would have another one right here, right? And we say its size is roughly that picture. Okay? Okay. A metal loses its valence electron. So look at the screen. When it becomes an ion, this shell disappears. So what happens to its size? It's smaller. Okay, we're ready to finish this sentence. Cations are smaller than their parent atom. Now, we do need to know the because. And it's in the picture, it's in the drawing, it's in what I said. But let's summarize it. Cations are smaller than their parent atoms because they abandoned their outer shell. So instead of having 3 shells, they just got rid of it. And now they just have 2. And then it's smaller. Fair enough? All right. Now, I know that you think, you're like, oh, it's 100% the opposite for anions. And part of it is, anions are larger. Whoops, I forgot an R up there, didn't I? Than their parent atoms. Okay, anions are larger than their parent atoms. True statement, 100% facts, as my son would say. But the explanation is not the same. Here's the reason why. Okay, there's one shell, and then I'm just going to put fat 1, 2, 3, 4, 5, 6. So this is oxygen, right? You with me? Oxygen is a nonmetal. It will gain 2 electrons, right? It will gain 2 electrons. We'll put them in green. 1, 2. And I know my spacing's off. Sorry, OCD kids. It gained 2. Did it gain an energy level? No. So we can't use the exact opposite. It did not gain. So why would it get bigger if it didn't add a shell? There's more electrons that do what to each other? They repel. Okay. This term, it's short. I don't know. It is called electron repulsion. Anions are larger than their parent atoms because of electron repulsion. The more electrons you have, the more space they must occupy because they push everyone around. Okay, you can see that at the dance. The more people that come, the more space we need. It's just common sense, right? And they push each other around. We okay with that? Sorry, I skipped that. It's not usually the hardest concept. If you gain an electron, you're bigger. If you lose one, you're smaller. That actually does make sense. There's some things in chemistry that are reversed, but this one's just not. Okay. We're not going to worry about the trend on this one, like from left to right or whatever. We just care about how they compare to their parent atoms. And the parent means the non-ion. So Na versus Na plus. Na is the parent, Na plus is the cation. Okay. Oh, well, let me just drag this so it's in order in the future. So this is just showing you the trend in size. So rubidium is 2.11 angstrom. Angstrom's A with a 0 over the top of it. We don't use it a ton. And helium is 0.32 angstrom. Just small, big. Very much so. 7 times-ish. 7 times this bigger, which makes a huge difference when it comes to reactivity. Okay.
Wait, so it's helium smaller than hydrogen?
Yep. They're about the same exact size, but it has 2 protons that are pulling the electron, and it has another one, but they're not in between the electron and the nucleus, but they're almost exactly the same. It's 0.32 and 0.32. Yeah, that doesn't make any sense. Not at all. All right. Next. So summary, you have that on there, right? Zeph is the attractive force. We've said that. We said this. The bold is the new one. The size of atoms increases as we move down in a family because we add principal energy level or shells. And I put it in real small, there is some electron repulsion. But ultimately, the up and down, the reason is you're adding or removing shells. Okay, the size of an atom decreases as we move from the left to the right because Zeph is increasing. Zeph and size are inversely proportional. So pulling the outermost electron closer to the nucleus. Due to the above rules, metals are generally large and non-metals are generally small. Yes.
So, like, following the rule that Zeph is
Inversely proportional.
does that mean that the elements that are higher up also have a higher Zeph?
We just treat them all in the same row, but yes, but ignore that one. Because the shells make a way bigger difference than the change in the Zeph. So for a row, we just go 1 through 8. The next row, we still go 1 through 8. Now, technically, is it slightly different? It is, but not one that we're going to worry about. All right. Our next item of business is ionization energy. Ionization energy. So we'll finish this topic. And we didn't get through all of chapter 7, but we got dang close. We just have a couple more and they're short. Ionization energy is really important. The definition, ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. Don't worry a ton about that besides the energy required to remove an electron. And it's going to be its valence electron at first. So, well, it's right here. The first ionization energy is that energy required to remove the first electron. Okay, so if I had 1s2, 2s1, I'm talking about lithium, correct? IE1 would mean the removal of this valence electron. You okay with that? IE2 would mean removing one of the S's. IE3 would mean removing the third. Easy enough. All right. Second ionization energy is the energy required to remove the second electron. It's not supposed to be way complicated there. This is very important. It requires more energy to remove each successive electron. All right, is that chart too small for you to read? So look here. Sodium takes 495 joules to remove its first electron. The second one takes 4,562. Takes 10 times more energy to remove the second electron from sodium than the first. And that should make sense. Sodium has how many valence electrons? 1. So that one's easy to get rid of. But then sodium becomes like what atom? Neon, which is a noble gas. and you don't mess with noble gases. Takes 10 times the amount of energy to mess up a full set of electrons than just one extra. We just put in a ton of energy. You just have to heat it or radiate it. It can happen. What about the next one? It's going to be like 5,000, but not another 10 times lead, because now we're already in there. Okay, magnesium. First one, now magnesium's in family 2, right? First one, 738, which is more than sodium, which was 495. Tell your partner why. It takes more energy to remove the first from Mg than the first from Na. I'm looking for a 2-word answer. Higher Zeph. That's all I'm looking for. Or more Zeph, or a greater Zeph. All those things. Look, magnesium is holding on with a +2, right? +1. Now, they're not direct relationships, so don't expect this to be exactly twice 495. There's a whole lot of complex crap in there, but it's good enough. So magnesium pulls harder. So here we go. First one, some energy, 738. Second one, 14. Third one, 7732. Huge jump here. Tell your partner why. Okay. Don't use the word Zeph in that answer. It's annoying. Does Zeph have anything to do with that answer? No. The third one is removing a what electron? A core. You could say a new shell. Whoever said that, that's fine. It takes more energy to remove a core electron, way more than a valence. Okay, last thing from this chart. Why this second one was still a valence electron, right? Why did it take more energy to get rid of that than the first one? Okay, good. There's less repulsion. The answer, the short answer is you're taking an electron from an increasingly positive atom. If I remove one negative, it becomes positive, right? And to remove a negative from a more positive thing takes more energy. So ionization energy, until you get to the core, it increases because you're removing an electron from an increasingly more positive thing. Okay, here we go. They're all on here. I know all of them. Okay. This one, it takes more because the atom's becoming more positive as you remove an electron. Next, when you've taken all of them, it takes a quantum leap. And that's a poor use of words, but it's one that they use. It means it goes up a ton. Now, it's weird because in chemistry, quantum means small, but whatever. It means you went from 495 to 4,000. That's a big difference. All right. And that's because more energy is required to move a core electron than a valence electron. This would be why noble gases do not react. This would be why sodium is very reactive. It takes 4,000 to react with neon, 495 to react with sodium. It's a huge difference. We'll talk more. Okay, you guys are awesome. I know today was overwhelming, but we'll wrap it up and hopefully feel good tomorrow. Okay, Aisley, I hope everything went well. Thanks for joining.